Okay, we are finally back 207 days later, but we'll pretend that those 7 months or so didn't happen. And we will continue our calculus playlist with integration by parts. Probably the most useful and annoying integration solving method that we will encounter, at least for now. Integration by parts is very, very useful, because quite a lot of the time, you will find functions that look like this. Example given here, x times by cos x, and we're trying to find the integral of that. Up until this point, substitution and reverse chain rule and all of that don't really help us here. We have two completely different functions that are multiplied together. If we think back to our product rule for differentiation, it's looking quite similar. And luckily, there is a reverse product rule. Unlike the reverse chain rule, which we've already discussed does not exist, there is a way to reverse the product rule and get a nice equation that we can use all of the time. Now, there are of course some intricacies there and some things that we need to be careful about, but in general, it is a nice, simple way to reverse the product rule. So I'm going to rub this out for now. We will come back to that example later, but first of all, let's actually prove it. You may have already seen the equation for integration by parts, but you probably haven't seen the proof. And the proof is very, very simple. If I have a function, u, multiplied by a function of v, or f of x and g of x, if you prefer that kind of notation, and I want to differentiate that, the derivative of u times v, and they're both functions of x, of course, I know I'm going to want to use the product rule. And I know that the product rule is the derivative of the first one, so du by dx, times by the other one, so times by v, plus the derivative of the second one, so dv by dx, times by the first one, u. Or the other way around, doesn't matter, there's a plus sign in the middle. So, get rid of that. This is my product rule. This shouldn't be anything too crazy. What I'm going to do is I'm going to rearrange this product rule for this guy right here. So u times dv by dx is equal to d by dx of uv. Yeah, u's and v's are a terrible idea when you've got this kind of handwriting. uv minus du by dx times by v. So I've just rearranged it into this form here. Now I'm going to integrate the entire thing. So I'm going to put a massive integral sign over the entire equation. Luckily, whenever I do this with an integral sign, I can simply integrate each component separately, right? I can do that because all I've got going on are pluses and minuses, or only minuses. So I can integrate the left-hand side, so u dv by dx is equal to the integral of d by dx of uv minus the integral of du by dx times by v, obviously the dx on the end there. Now this, if you've been studying this before, might start to look very similar. Familiar. And that is because we have just come up with my rule for integration by parts. The only thing in here that might not look familiar, that I need to simplify, is this guy here. In here, I have got the integral of a general d by dx. Different to having the integral of a du by dx or the integral of a dv by dx, because I don't have any information about these variables here. But in this one, I've just got the integral of a general d by dx. And hopefully, we know by this point that the integral of just d by dx, they cancel out. It's the same as dividing and multiplying. They're inverse, you know, taking a log and raising it to an e. They're the inverse of one another. So my integral and my d by dx cancel each other out, and I'm simply left with a uv. And this here is my integration by parts rule. But let's get into a bit more detail as to what that actually means. So this here is my final integration by parts formula. This is what we're going to be popping all of our information into to be able to integrate something that looks like one function times by another function. And this is what I want to zoom in on. And I'm going to go back to my old example from 5 minutes ago of x cos x. So I know I'm trying to integrate something multiplied by something. Well, in this formula, yeah, I've got something multiplied by something there, but there's no integral. I've also got it there, but it's a bit tricky on that side. Could rearrange it, can't be bothered. I'm just going to use here. I have got the integral of u multiplied by dv by dx. So what I'm essentially going to have to map is this idea that one of these two functions is going to be u, and one of them is going to be dv by dx. What that means is I am not starting off with two standard functions of x. The same way the product rule just starts with a function times by a function, which is obviously hidden up here. I don't have that. I have got a function, u, multiplied by the derivative of another function. So to make this a bit simpler, we're going to draw a little table. And this is what we want to do every single time we encounter something like this. I'm going to draw a little table with a u, du by dx, a v, and a dv by dx. These are the four things that are in my equation, and these are the four things that I need to know. I've got a u, a dv by dx, a v, and a du by dx. These are the four things that need to get popped into this equation up here. Now, I know it is these two, the u and the dv by dx, that exist inside my function here. One of these is the u, one of these is the dv by dx. Now, we're going to have a look at how to decide which is which in a moment, but for now, just believe me when I say we're going to take my u as the x and the dv by dx as the cos x. Again, we will get onto how to decide which is which in a second because it is very, very important. And now we can fill in what the other two are going to be. So du by dx, well, that's just the derivative of x. Well, the derivative of x is 1. And this v, well, that's the integral of dv by dx, which is the integral of cos, right? Well, cos differentiates into negative sign, so cos is going to integrate into positive sign. And I've got all four of these laid out. And because I've got all four of these laid out, I'm just going to erase this so I have enough room to work with. I can fill out this entire equation. So, starting on the left, I've got the integral of u times dv by dx. Well, that's just the integral of x cos x. I know that, that's what I'm trying to figure out. Dx is going to be equal to u times v, well, that is x times sine x, minus the integral of v, which is sine x, times by du by dx, which is 1. So times by 1, just throw the dx on the end there. Now, we do have to do another integral, right? Our equation has an integration sign in it. We're going to have to do that. So I've got x sine x minus the integral of sine. Well, once again, cos differentiates into negative sine. So sine integrates into negative cos. So I've got minus cos. I've got plus cos. Obviously, include the plus c on the end. I've never forgotten. And we have got my answer to the integral of x cos x. Now, it is this integration here that poses the biggest troubles for us when we're doing our integration by parts. Let me show you what I mean by that. So I'm going to keep the same example, but I'm going to swap. So I'm still doing x cos x, the integral of x cos x, but instead of having u as x, I'm going to put my u as cos x. You know, what if we just changed our mind, we did it the other way around? And our dv by dx as x. Okay, so I've just flipped them around. I've made a different decision. Let's fill up the table. So du by dx, well, cos differentiates into negative sine. I don't know how many times I'm saying that in this video. And dv by dx is x, so v is the integral of that, well, the integral of x is x squared over 2. And yes, you could technically put a plus c in here, but it doesn't really matter. The plus c's will even out at the end, so I wouldn't worry too much about that. But if you want to be thorough, yes, there should be a plus c here. Okay, right, let's put it all into the formula. So uv, well, cos x times x squared over 2. It's already looking a bit more messy, but you know, that's not necessarily a bad thing. Minus the integral of v, that's x squared over 2, times by du by dx, which is minus sine x. So I'm going to bring the minus out, and I get this. Now, this is where our issue lies. This cos x squared over 2, yeah, it doesn't look very pretty, but let's be honest, integration usually doesn't. So that's not really my concern. My concern is this thing. The integral of x squared over 2 times by sine x. Now, in the previous example, when I had these flipped, this was just the integral of cos, right? That was nice. But now, just the integral of sine. But now, I've got this nonsense. I've got this x squared over 2 and all that rubbish. And if I were just to give you that integral on its own and ask you how to solve it, well, you have to solve it using integration by parts. We're stuck in a loop. We're stuck in a loop because now this integral isn't just something easy. It's something we're going to have to do by parts again. Now, fair warning, sometimes the only way through a question is to do integration by parts twice. Sometimes it's 3 times, less likely at this certain level. Sometimes you might need to do it 4 times. Hopefully you never do. I doubt you ever would. But in general, if we get to a point where we have to do integration by parts within an integration by parts, something's gone horribly wrong. Usually the thing that has gone horribly wrong is our decision here. The difference between what we did last time and what we did this time is with this x. This cos doesn't really matter. No matter where I put this cos, it's turning into a sine. If I differentiate it, it's turning into a minus sign. If I integrate it, it's turning into a regular sign. No matter where I put it, it doesn't matter. I've got a sign either way. Yeah, the minus is different, but who cares about a minus sign? But this x, if I put him up here and I differentiate it, it turns into a 1. It essentially disappears. My x component is no more. It's a 1. But if I put it down here, it turns into an x squared over 2. No one wants to be dealing with an x squared over 2. So, the very bare basics of this is you want to try and get rid of one of the variables. Usually that's only possible if you have an x. If both of these were, say, a cos x and a e to the x, right, simple, cos x and an e to the x, this isn't going to happen because you're never going to get rid of either of them. The cos, no matter where it goes, is going to flip between a cos and a sine and a cos and a sine and a cos and a sine. Doesn't matter. The e to the x is just going to stay how it is no matter where you put it. But when we've just got an x on its own, well, I can get rid of it. How do I get rid of it? By putting it up here.